Okay, so let's do the true or false in this question. The first one is the particle in a box ground state has quantum number n equals zero. That is clearly false. The minimum value is n equals one. Because n equals zero implies the energy is zero, which eventually will mean the wave function zero everywhere, which is not true. You have a particle in the box, it's there. Um, so it doesn't make sense to have zero. So the lowest energy state is doesn't correspond to a quantum number zero, it corresponds to a quantum number one. The particle in a box stationary state wave functions are discontinuous at certain points. No, the answer is false. They are continuous at all points. Um, so that's going to be false. The next one is the first derivative of each particle in a box stationary state wave function is discontinuous at certain points. So if we take a look at, um, let's see, figure 2.3, yeah. So if you go to, let's just take a look at the wave function, right? So the question B said the wave functions are discontinuous. Now, if you take a look at the wave function sketched into the 2.3, you see that there is no discontinuity. However, if we have to take a derivative of uh, these wave functions, we will see that at x equals 0 and x equals L, L being the width of the box. So at the ends of the box, the derivative is going to be discontinuous. The wave function still is, but the derivative is. So this statement is actually true. Now let's go to the next one, which is the maximum probability density for every particle in a box stationary state is at the center of the box. No, that is false. If we were to refer back to that figure again, figure 2.3, we see that, actually figure 2.4, we see that the probability density is maximum at the center for n equals 1 quantum number. We actually have a node at n equals 2. I think we also have a node at n equals 4 and so on, even quantum numbers. So no, that's not true for all of the states. The nodes are present there. The maximum of the probability density does keep changing with the quantum number you're looking at. So for E, for particle in a box n equals 2, the probability of finding the particle in the left quarter of the box equals the probability of finding it in the right quarter of the box. That is definitely true. We can take a look at figure 2.4 and you see that the probability density is actually equal. We don't need to evaluate any intervals to arrive at that conclusion. So let's go to the next statement. It says for n equals 1 state, the probability of finding the particle in the left third of the box equals the probability of finding it in the middle third. So okay, you know what, let's just do this. So if we have something like this, no, we are not evaluating particle. If we were to divide it into like 3 equal parts, this will be the left third, right? The middle third is going to be this. So this probability is not the same as this probability. Those are that is less than the probability of finding it in the middle third. So the answer to this is false. Moving on to the next statement. The wavelength of absorption, uh, the wavelength of absorption transition from point number n to n+1 decreases as the value of quantum number n increases. That is true, and let's see why. Because your energy is proportional to n squared, right? What is energy? Energy is n squared, 8 squared over 8 10,000. So your energy is proportional to n squared. So the change in energy as you go from n to n+1 is going to be n squared um, n+1 squared minus n squared. It's going to be proportional to this. And this is nothing but 2n+1. So the change in energy is proportional to n, right? So as the quantum number increases, as you go from 1n to a higher n, the energy increases, right? And energy is nothing but this, your energy is inversely proportional to the wave. So as the energy increases, the wavelength decreases. So the statement given in G about the wavelength decreasing as the quantum number increasing is actually true. So yeah, G is true. Now let's go to the next statement. The probability density for the particle in the box stationary states is constant along the length of the box. No, that is false. The probability density is not the same for the entire box. And that is, no, we were not dealing with classical mechanics here. This is quantum mechanics clearly, and no, the probability is very different. Take a look at figures 2.3 and 2.4, where 2.4 specifically, because that's where the probability density. You see how it changes as you move along the box. You can find a particle, for example, at n equals 2, you can find a particle in the left half of the box and the right half of the box, but you can never find at the center. So no, the probability density is not the same as you move along the width of the box or the length of the box. Sorry, I think, yeah, along the width it's not the same, but even along, I think they mean, yeah, length and width. Yeah, it's the same. I believe so. A quantum mechanical, let's go to the next one. A quantum mechanical particle in a box has a ground state energy that's greater than the lowest possible energy of a classical mechanical particle in a box. That is actually true. In classical mechanics, the lowest energy you can have is actually 0. However, in quantum mechanics, the lowest energy you have is this. Yeah. So they're not the, yeah, they're not, and the answer is true. The energy is actually greater than 0, but here you can have 0 and plus. So quantum mechanically, yes, your energy is greater, and the statement is true.